this is an opinion. I think it's easily the worst. I don't think there's even anything that's remotely comparable to that, because trig substitution itself is kind of complicated. And the object of trig substitution is to give you a new integral that may have parts, or it won't have partial fractions. I've never seen one do that. But I have seen trig substitution results in integration by parts or U substitution. And so it can get quite ugly and hairy. But anyway, so I'm going to get rid of that page. I don't need that anymore. These are the problems I wanted to start with today. My screen's frozen. You can't see squat. There. Those are the problems I wanted to start with today. I will go ahead and tell you numbers 2, 4, and 6 are trig substitution. The first 3 are trig substitution. After that, it's just a hodgepodge. You might need trig substitution. You might not. It could be parts, substitution, just recognition. Who knows? So the rest of them, and that's really where the challenge is with integration. If trig substitution, as bad as it sucks, if I tell you it's trig substitution and you know what approach to use, it takes a lot of the anxiety away from integration. Where a lot of people struggle is looking at something like number 11. Number 11, you actually could use trig substitution. It'll work. But is there another option? And so that's where people have a hard time, is figuring out what technique to use in which situation. So I think what I'm going to do is, I don't know, you know, let's do 2, 4, and 6 together. Let's go ahead and do those 3. Because those are the new ones, those are the trig sub ones. And then after that, I'm just going to be quiet and let you work on the rest of them. We did yesterday start some multiple choice questions out of a Barron's, I forgot what the title of it was, but there were like 80 questions on the PDF, and I hand selected a few of them. We're going to finish those also. And whatever we don't finish in class is going to be homework. So get as much done in class as you can. That'll be less you have to do tonight, and then tomorrow, who knows what we'll do. But we have now covered everything that is fair game for the next test. We have completed all integration techniques. There are no more that we are going to learn in this class. More do exist, but not in BC. So let's start with number 2. By the way, this comes from a PDF that is on my webpage, and it's actually not a bad one. That's not y'all. BC, here we are. Integration practice, all types. There are a lot of problems here, and down here are all the answers. So this is not a bad sheet for you to look at, like even ones that we don't do. If you want to go back and look at them for studying and just to kind of practice, you can see them. 32, I think it was. There was an error in the problem that I wrote originally. Sine x over 1 plus x squared. I don't know what I was doing, but it doesn't work. There are some functions that do not have an antiderivative. Well, not in the world of elementary functions like we're familiar with. So sometimes you cannot find an antiderivative, although every function does have a derivative. Okay, so let's do number 2. Let's do number 2, and I've already told you that it's trig sub, so that takes some of the guesswork out.
Mr. Carboni, you're
not. What? What'd I do?
You're not presenting your screen.
You're not presenting your screen. I thought I was. Oh, I know what happened. I started presenting my screen originally, and then I locked my computer for a minute. And I guess when I lock my computer, it quits showing my screen. Okay. Sorry about that. Thank you. And I am recording, though, at least. Okay, so number 2, to choose the correct trig substitution, you're looking at the thing that has like x squared plus or minus a number in some way. So x squared plus 1 looks a whole lot like the identity tangent squared plus 1 equals secant squared. And that's the identity we're going to take advantage of here. So I'm going to take out the x, replace it with a tangent. But before I do that, before I substitute the x's in, just like with u substitution, you have to take care of the dx first. You have to take care of that, and that's probably the number 1 mistake people make. If they know how to do trig sub, that's where they'll get careless. They'll forget the dx part. So if x is the tangent of theta, what would dx be? Secant squared theta, d theta. And so I have to substitute the dx first. Make sure you take care of that, then substitute everything else. Now, the way trig sub works is it really doesn't matter what order you do it. Just make sure you remember to account for the dx. So I'm going to go ahead and do both at the same time. So that's going to be, look how sexy that squiggle s is. I have to say, that's a really nice one. I don't want to turn it upside down because it's going to ruin it's going to ruin my happiness. So we're just going to leave it like that. The bottom's always a little bit bigger than the top. Nothing wrong with the big bottom, though. All right. So we have 1 over tangent squared theta squirt tangent squared theta plus 1. And then my dx is going to turn into a secant squared theta d theta. All right, and we're taking advantage of that Pythagorean identity. Now here's where we usually get a lot of simplifying. Nothing cancels yet, but I do know that tangent squared plus 1 is equal to secant squared, right? And that's really the square root of secant squared, which is secant to the first. So all of this will cancel with one of these secants up here. And this integral reduces to secant theta over tangent squared theta, d theta. We good? Now, hopefully, what you have just created, even though it has trig in it, which is kind of something we're not too happy with, hopefully we've created an antiderivative that we now can do something with. And we kind of reset, like we just forget everything we've done so far. It's a whole new problem. So if I gave you this as the initial antiderivative, what would you do? Okay, go down the list. It's not power rule and it's not recognition. I'm going to try u sub. Is there a way I can do a u sub? It almost is, but the problem is secant squared is the derivative of tangent. Right? I don't have a secant squared up there. If that were secant squared over tangent squared, I've got something to work with. But I don't. So now I'm going to manipulate this thing. I'm going to turn them all into sines and cosines. So secant is the same thing as 1 over cosine, right? Right? That's cotangent. Like if I bring that tangent up, it's cotangent squared, which is cosine squared over sine squared. Is that right? I did a lot in one step there. Is that dangerous? I can cancel the cosines, and now I do. Oh, that was supposed to be red. Everybody knows you cancel in red. It's like the blood of the fallen mathematical expression. Slash you out of the way. Sorry, I got a little bit carried away. Now I see something and its derivative. Cosine is the derivative of sine, right? Now we finally have our u sub. U is sine theta. Du is cosine theta. No changes needed, right? I don't need to throw in a negative. It's ready to go. So this will turn into the antiderivative of 1 over u squared du. Now we have a new answer. So we've had to do 2 substitutions. How do you integrate 1 over u squared? Yeah. If you say natural log of u squared, I'm going to bite you. The top is not the derivative. By the way, that's just a very common mistake. People see 1 over and they assume natural log. Don't do that. I don't know if anybody's doing that. I've tried to avoid anyway, whatever. So I'll bring that up as u to the -2. The antiderivative of that would be u to the -1 over -1, right? Which is the same thing as -1 over u. Now we have to work and get this back into x's. So first I'm going to go from u to theta. So this is going to be -1 over sine theta plus c. Do I need to stop? Yeah. Good. So I've got my antiderivative in terms of sine theta, but now I've got to get out of sine theta and turn it back into x's. And this is where we did that weird triangle thing. If tangent is equal to x over 1, tangent is opposite over adjacent. Using our old friend SOHCAHTOA, Sacagawea's sister. Have we not talked about her before? I thought we have. Have we not talked about SOHCAHTOA yet? SOHCAHTOA was Lewis and Clark's math tutor. Okay, so I draw a triangle. I can put theta wherever I want, at least on one of the acute angles. I always put it in this lower left hand. Tangent theta being x over 1 means the opposite side will be x, the adjacent side will be 1. Pythagorean theorem would tell you that this would be the square root of a squared plus b squared, which is x squared plus 1 squared, right? Right? And you should, the expression you have under the radical should resemble or should be what you initially looked at that triggered your trig sub thought process. So I got square root of x squared plus 1. I have x squared plus 1 up here, so I like what I see. Good. And then I need sine of theta. Sine will be opposite over adjacent. No, it's not. Opposite over hypotenuse, right? And so that would be, if you don't want to simplify it much, you could say -1 over, and sine would be x over root x squared plus 1 plus c. And if you do want to clean that up, that would be negative root x squared plus 1 over x plus c. Woo! Usually 1. But this wouldn't show up in a free response. Now, there are free response problems where there is a C involved, and it's like a 1-point penalty that sometimes carries with it. If you don't have the plus C written, you don't get any subsequent points either, depending on if they give you information that allows you to solve for C. But that kind of makes sense because if you don't write C, then you're obviously not going to solve for it anyway. And that's actually going to be one of our last units that we'll talk about that context. You need to add it when you take the integral, because sometimes there's the C at the point of taking the antiderivative, the C becomes a permanent fixture of the problem. And if there's algebra involved, sometimes that C ultimately ends up in the denominator or inside a radical. And if you just do the algebra first and then slap a plus C on the outside, it may not actually end up being where it should have been had you put the C in the right place at the beginning. If that makes any sense. It's really hard to talk about math theoretically like that. You do need to remember the plus C the instant you take the antiderivative. Number 4. What was that? Within a limacon? We've done that already, hadn't we? Have we done area? Oh, we haven't done areas of polars yet, have we? We're gonna. That's our next unit, actually. So right now we're only finding how to do antiderivatives. Our next unit is using antiderivatives for bigger questions. So that would involve areas. You have to subtract it out. You have to account for where the loop begins and ends and subtract it out. So that's one of those BC specific concepts that y'all signed up for. Suckers. All right. So here, 1 plus x squared, this almost looks recognition, doesn't it? Almost. You know what we could do? We could just get a little eraser or some white out, and let's get rid of the bottom part of this, but get rid of the top part. And now we have inverse sine. Oh, geez. All right. It looks recognition, but it's not. There is not enough information to even attempt a U sub. There's nothing else outside the radical that would help you. So this is a trig sub, and this is another. We did tangent on the last one, didn't we? This is another tangent one. X is tangent theta. Dx would be secant squared theta. D theta. Oh, I think I know where this one's going to go. Okay. And so when I substitute that, the dx is secant squared. I like to put my d theta over here. You can stick it in the numerator if you want, over the squirt of 1 plus tangent squared. And this one cleans up to something very nice and clean. 1 plus tangent squared, the square root of 1 plus tangent squared, all of that is secant. And that will cancel one of the secants in the numerator, leaving you with just the antiderivative of secant theta. I believe, if I'm not wrong, I still believe, even if I am wrong, I believe this. We have not run into a problem that is just secant theta yet. I've talked about it briefly. It was on the sheet of integration problems, and I told you there's 38 of them there, but only 6 of them were worth memorizing. This was one of them. This is one of them. Technically, the antiderivative of secant theta is a U substitution problem. You know what U would be? If anybody guesses it, I'll be without Googling it, I would be amazed. I'm gonna show you how this works only once, and then after this, it's better for you just to memorize it. I'm gonna move my d theta over here. Now, you all agree that I could write this as a fraction by putting it over 1, right? And if I wanted to, I could do something crazy like multiply the top and bottom by theta. As long as I do the top and bottom the same, I have preserved the value of the fraction. I haven't altered anything. It looks weird, but I can do that, right? I'm going to do this. I'm going to multiply the top by secant theta plus tangent theta. This is why I was saying I would be shocked if anybody thought of this on their own. And I'm going to do the same thing with the bottom. If I distribute through the top, we get secant squared theta plus tangent squared theta. No, we don't. Plus secant tangent theta. Do those two look familiar? They damn well better. All right? The denominator is secant theta plus tangent theta. And at this point, I expect you to be able to spit out the answer to that antiderivative immediately. Why? It's a fraction. Every time I have an antiderivative that's a fraction, I always look for one thing first, because it takes about a second to think about it. Is the top the derivative of the bottom? Because if it is, that's a natural log. It is. Derivative of tangent is secant squared, derivative of secant is secant tangent. Therefore, the antiderivative of secant theta is just the natural log of secant theta plus tangent theta. Now, that's a really weird process, isn't it? Like just this random, hey, I'm going to multiply by secant plus tangent on top and bottom. It's kind of a bizarre out of left field thought process that does work, and it is the correct way to do that antiderivative, but I don't expect y'all to work that out. So I would say, just remember that the antiderivative of secant is the natural log of secant theta plus tangent theta. Okay, good. By the way, the natural log of cosecant theta is a very similar mechanism that I would also recommend you just memorize. And they're all on that sheet that I gave you a long time ago. All right, so there's our antiderivative of secant. I didn't grab the plus c or the closed absolute values. So I'll move this over here. Oh, man. And now we have to turn this back into thetas. I'm sorry, x's. There we go. So I need to draw the triangle. Exact same triangle we had for the last problem. If tangent theta is x over 1, then I have a triangle. Right angle here, opposite x, adjacent 1, hypotenuse root x squared plus 1, or 1 plus x squared, whatever. And I need the natural log of secant theta plus tangent theta. So my final answer is natural log of secant would be the reciprocal of cosine. So that'll be root x squared plus 1 over 1. And tangent theta is just x plus c. There's your answer. Shiny, happy people? The good thing about trig substitution is it kind of forces you to review pretty much everything else also. Your trig identities, your u subs. We haven't done one that resulted in parts yet. And I honestly don't know if I chose that for number 6. I did say I wanted you to do number 6, but I can't remember if number 6 does that. Okay, number 6. The last one where I am telling you the technique to use, which will be trig substitution again. Okay, so what identity am I going to take advantage of this time? Not secant, no, because the number's first. So secant squared minus 1 is an identity, but I need it the other way around. I need number minus trig. That would be 1 minus sine squared is cosine squared. Except this is 4, so I need to have 4 minus 4 sine squared to make this work out. So I'm going to plug in 2 sine theta for my x. My dx is going to be 2 cosine theta, d theta. And we'll substitute that in. So I have a fraction, dx is 2 cosine theta, d theta. X squared is going to be 4 sine squared theta, the square root of 4 minus 4 sine squared theta. D theta, I'll stop and give you a second to catch up. We good? What's that? Do I have it? No, that was a typo. No, 1 d theta. You will only have 2. Those are called the differential parts, the differential. You'll only have 2 like d thetas or dx's when you're into double integrals, which is not a BC concept. That's like beyond Cal 2. I think that's Cal 3 stuff when you get into double integrals. And in that case, it's like different variables. It's like a dx dy thing. Let's see. So cleaning this up. This cleans up kind of nicely because the square root of 4 minus 4 sine squared theta is going to end up being 2 cosine theta. And then that can cancel with the 2 cosine theta in the numerator. The 1 over 4 I don't think is helping me any, so I'm going to pull that 1/4 out, and I have 1 over sine squared theta. What do you think of that one? I like this one. Yeah. I'm going to change that to 1/4. Now, typically we'd like to steer things in the direction of sine and cosine because we're more comfortable with those. But the reciprocal of sine squared is cosecant squared. And in the world of antiderivatives, that is highly desirable because that is the derivative of cotangent, right? Except for the negative. So the answer is negative 1/4 cotangent theta plus c. Of the 3 of them, this may end up being the easiest one. I know that x is 2 sine theta, so sine theta is x over 2, and we'll draw a triangle to help me decipher that. Sine is opposite over hypotenuse. Pythagorean theorem would be the square root of hypotenuse squared minus leg squared, so 4 minus x squared. Look back up at the problem, and that's what I started with, so I feel good about it. And cotangent, the reciprocal of tangent, so my answer will end up being negative 1/4, and cotangent will be root 4 minus x squared over x plus c. Do we feel accomplished? Yeah. Okay. Then what I'm going to do, I'm going to turn y'all loose and see what y'all can do with these other 8. Some of them, I'm looking at 2 of them should be almost instant. The rest of them may take a little bit of thought. Where did 4 go? I cut it out. I'm supposed to copy, not cut. Stupid. Paste. There we go. By the way, which 2 do you think should be instantaneous? Like you look at them and you spit out the answer instantly. 8 is one of them. Almost. I think there's too much arithmetic involved in 30 that you should be able to look at it and just spit out the final answer because that's a definite integral. Now the antiderivative, sure. But there's one other that should be instant. Oh, come on. You're breaking my heart here. I could go with 15, but 15 is a U sub problem. 16 people, come on, what is 16? That's the derivative of arctangent. Yeah. Now here's if there is such a thing about that's good about trig substitution, if you forget your inverse trig derivatives, you could use trig substitution to work around it. You would do a substitution where x is tangent theta, and it'll end up being really nice. But that's a lot of work. So I'm going to just leave y'all alone for a minute, and then if y'all have questions, if there's one that you run into that scares you, I will help you out. I don't think I posted attendance yet today. let's see, second period. He's already marked. Oh, take that. So who's not here? Wyatt, and wasn't there one more? Yang, who's also marked absent. Okay. Have we finished them? How did number 10 go? What's the first step in number 10? Actually, there's two ways to do 10. Have y'all finished 10? You skipped it? You son of a... All right. Golly. You can dub sub it. Two ways to do this. You can do U sub. I wouldn't recommend it because there's an easier way. But if you did U sub, I've always told you in U substitution, as long as you can account for the DU, then you have the green light to keep going. And I do see the DU in there, so I can try this. The DX will become my DU. Oh, whatever, I'll just leave it. That's ugly. The DX is my DU. I have U in the denominator, but on top, I still have an X squared that's not accounted for, right? But you could substitute U minus 1 in for X and make this U minus 1 squared, right? All right. Now, to make this work, you're going to have to expand the numerator. U squared minus 2U minus 1 all over U. Plus 1, thank you. And then STD it. U squared over U is U. 2U over U is 2. 1 over U I will not change because I recognize that as a natural log. So the answer is U squared over 2 minus 2U plus natural log U. And then you could substitute in, right? That would work. That's not the way I would recommend you doing it, because when you substitute, you'll end up with X plus 1 squared over 2 minus 2 times X plus 1 plus natural log of X plus 1 plus C. However, if this were multiple choice, which these problems are typically multiple choice on the AP exam, they're very seldom free response where you're just finding antiderivatives like this. The answer in multiple choice would likely be not that, but something very similar. It'd likely be that. Or some variation of that. Could actually be even different, more different than that. Actually, I could see it being different. So what in the world did I do? Like, how could I? Yeah, so if you distribute this -2 through the x plus 1, you have -2x minus 2, and that -2 could be absorbed into the unknown constant to create a different c in the end. And so that could happen. Now, that said, I still, even though that does work, I still wouldn't do that because I did tell you once upon a time that if you ever are integrating a rational function by definition means numerator and denominator are polynomials. You need the top degree to be less than the denominator. Less than, not equal, but less than. And in this case, it is not. So if I were doing number 10, first thing I would do is I would divide the bottom end of the top. I would use synthetic. 1x squared, 0x, 0, bring down the 1. And I'm going to use synthetic division. And this turns into the antiderivative of 1x minus 1 plus a remainder of 1. So it'll be 1 over x plus 1. Right? And that antiderivative should be easier because we have a power rule for the first two. X squared over 2 minus x. The top is the derivative of the bottom in that fraction. So natural log of x plus 1. That's probably, if this were multiple choice, that's probably what the answer would be in multiple choice. So if you went the dub sub route, you're going to wonder how in the world can I get from this to that? And so we actually have more algebra to do. And what you could do, if you expand x plus 1 squared, use an STD, you're going to end up with another constant that once again gets warped into the plus c. And so you could manipulate it to the right answer, but you're just creating a lot of work because you did not divide at the beginning. So if you ever see a rational function and the top degree is not less than, if it is equal to or greater than the bottom, you need to divide first. Divide first and then look at what's created. It's usually not only the shorter way, but usually the way that they will approach it when they write their answers for the AP exam. Yeah, that's exactly why I chose number 10, because I figured y'all wouldn't remember to divide that. By the way, what do we have? 9 minutes? We got 50 or 55? I never remember. Okay, we got plenty of time. Do you want to go through really quick and just talk about what technique you would use for each of them? Okay, so number 11, what would you use? U sub, because x is almost the derivative of x squared minus 1. All we need is a 2, so we could U sub that. Trig sub will work. So if you hate yourself or if you just want to practice trig sub, you could do that. 15? What is U? Yeah, so the 1 over x is the du, right? And that's one of those things a long time ago, I called that a hidden du, because your u is not a fraction, but its derivative is. If u is the natural log of x, its derivative will be 1 over x dx, which is there. So that's a u sub. 16, recognition. Trig sub will work, but don't. 19 is a tricky one. 19 might be the hardest one of all of them that are remaining. Maybe even harder than 2, 4, and 6. 2, 4, and 6 were hard, but should we go ahead and do 19? 19 is parts. I think. But there's actually a few things I'm going to do first before I decide what integration technique to use. Really quick, let's talk about 22. What do you want to do for 22? Yeah, the ABC thing, partial fractions. And honestly, it doesn't matter if you know the name of it, as long as you can do it. They don't ask you vocab questions on the AP exam. So the bottom does factor, so partial fractions. If the bottom did not factor, then you would do the completing the square trick that we did a long time ago with inverse trigs. But those typically have only a number on top, not like x plus 5. What about 30? What about 30? 30, I'm trying to trick you. Yeah, the top is the derivative of the bottom. So you should be able to spit out the antiderivative instantly, all right? Now, I wrote this one in a way that partial fractions does work. The bottom factors, if you want to do partial fractions, it will work. But the answer you get to partial fractions is the same thing you'll get if you just recognize at the very beginning that it's a natural log, right? So always, if you have a fraction, always look first, is the top the derivative of the bottom? Because it's a fleeting thought. You're not going to spend like 10 minutes trying to figure that out, I hope. Right. So on to number 19. On to number 19. Equals 2 pages of 10, yeah. So number 19, what do we think? I kind of gave you a little bit of a hint if you're paying very close attention to what I said a second ago. I did say parts, but I said there's some things I want to do to this before I choose my integration technique. In other words, some type of algebraic rewriting of it. And the reason is I don't like tangent squared. If I were to try parts, now the mnemonic was Liate. You always choose algebraic before trig, but that would leave you with tangents squared for your V prime. And I have absolutely no idea, off the top of my head, I might could figure it out, but I don't know how to very quickly integrate tangent squared. Actually, I just figured it out in my head. So, okay, so you can do it. But the process of doing that, you could do it here. It's easier because tangent squared is just kind of a weird thing. I don't recognize it. The antiderivative tangent squared is going to involve some other work. I'm going to rewrite this problem not as x times tangent squared, but x times secant squared theta minus 1. Because when I do that, I'm sorry, secant squared x, not theta. Because if I do that, now I've introduced a secant squared, which I do recognize. That's something I like. I'm going to distribute my x. And when you are integrating a sum or a difference, you look at them separately. And I very, very, very seldom do this, but I will in this case. The antiderivative of x secant squared x is significantly harder than the antiderivative of x. So I'm going to separate this into 2 antiderivatives so I can process them separately. So this is going to be the same thing as the antiderivative of x secant squared x minus the antiderivative of x. And now I've separated out the power rule. I like my parts on the left side better. All right, so now I'm going to do my parts. U is x, v prime is secant squared x, u prime is 1, v is tangent x. Can we do the shortcut? U double prime is 0, but that only works if you can do the antiderivative of tangent. You know the antiderivative of tangent? Probably not quickly right off the top of your head. Now, it's unavoidable. We're going to have to do the antiderivative of tangent anyway, because that's what the parts is going to leave us with. But sometimes it's better to rewrite it as its own integral. So this will be x plus tangent x. I'm sorry, x times tangent x minus the antiderivative of tangent x. So we still have to think about the antiderivative of tangent. We weren't escaping it by avoiding the shortcut thing. So we still have to do it. But sometimes it's easier to just write it out and kind of regroup and reprocess the problem. The antiderivative of x is x squared over 2. So I'm going to bring that down. I'll go ahead and put my plus c over here. And now we have the antiderivative of tangent. It's very quick. And I think I may have done it yesterday. Did I do it yesterday? That's right. It was in the multiple choice of those, the ones y'all had over the break, wasn't it? Yeah, rewrite that as sine x over cosine x. Right? And the top is the derivative of the bottom if you put a negative there. So the antiderivative of tangent is negative natural log cosine x plus c, but then my plus c is already in this problem. So there we are. X tangent x minus negative plus natural log of cosine x minus x squared over 2 plus c. And yeah, I'm going to stand by what I said a minute ago. That one is the hardest one of the remaining problems. You may still think the first 3 we did were harder, but we good? That was fun. See, how much time do we have left? 6-ish minutes. Is there another one in here that we want to do before we run home? And the multiple choice, yeah. which we did a handful of. I think I went through and I pulled some of the harder ones yesterday in that multiple choice. But yeah. Maybe 10, I think. 22? Yeah. I was thinking 22 also. What? I don't give a lot of homework. Actually, I really don't, do I? I need to start channeling my inner Reinsch. Okay, so this one always check, see if the top is the derivative of the bottom, but there's no way you can turn x plus 5 into a 2x plus 3. So we're going to go with partial fractions. X plus 5, the bottom does factor x plus 4, x minus 1, and that's going to equal something over x plus 4 plus something else over x minus 1. And if you were paying attention yesterday, if you tuned in or if you watched the Google Meet after the fact, I talked about this shortcut method, where if I want to know what a is, I find the value of x that makes what's under a equal to 0, and that's -4. And then I go to my original problem, and I block out the factor that's under the a. I block out the x plus 4, and I plug -4 into everything that is remaining. So my value of a is going to be -4 plus 5, which I think is 1, over -4 minus 1, which is -5. There's my a. Repeat for b. X equals 1 makes the factor under b equal to 0. So I go back to my original fraction. I block out the factor that is under the b, and I plug 1 into the remaining. So 1 plus 5 is 6. 1 plus 4 is 5. And so now I can rewrite my integral, antiderivative of a over x plus 4. So that's going to be -1/5 over x plus 4. Plus the antiderivative of b, which is 6/5 over x minus 1. And because of how nice College Board is in the world of partial fractions, if you encounter a partial fractions on the AP exam, it will end up a natural log. They're not going to give you the bizarre partial fraction things that have like quadratic factors and all that mess. So if I pull out my -1/5 and my 6/5, yes, sir, Parker. In that case, the numerator is going to be a now I'm talking specifically in the context of BC. If you see that in this class, the numerator will be a constant, and those are the problems where you like blocked off the x squared minus 8x or whatever, and you completed the square, and it turns it into an inverse, usually inverse tangent, but it turns it into an inverse trig. Okay. Let's see. So -1/5, and once I take that -1/5 out, the top is the derivative of the bottom. And then take out the 6/5, and top is the derivative of the bottom, natural log x minus 1. And then if it's convenient, which in this case it's not, if it's convenient, always think about properties of logs. Like if you're adding logs, you can combine them with multiplication or division if you're subtracting. In this case, it's going to be really tough because you would have to first move these up as exponents, which is just going to be really ugly. So chances are this would not be condensed in multiple choice world, so I would stop there with 22. Good? And don't forget the answers to these are on my webpage. And I think it's part of the PDF that the problems are on. So if you run into problems with the remaining ones that we haven't talked about in class, you can always go there and check the answers out and see if that jogs your memory. And you'll probably start to feel motivated and just go ahead and do all 32 problems on the sheet. And the answers to those are there as well. So I think I'm done. I don't have my Google Meet open over here. I wonder if they've been saying anything. Nope. All right. So you people at home, I don't know when I started recording. I know some of y'all started talking in the chat before I started recording. So if you said something early, you may want to say something again just to make sure that I know you were here, and y'all can go on home. Yep, we got 2 minutes.